As I wrote out these pages, I kind of came at this from two different directions. And on the one hand, I thought, well, of course, it's all really just matrix multiplication. The vector multiplication is just a special case of that. And I put this together and I thought, wow, this is really cool. When we think about this with multiple colors, all we're doing by multiplying A times B is we're making this grid, right? So if we've got a 3 by n matrix here and then an n by 4 matrix here, we end up with a 3 by 4 matrix as the output. And each part of that is going to get the row, each row is going to be the row from the matrix on the left, and each column is going to be getting terms from that matrix on the right. Okay, so then what's the rule for how we put that together? Well, actually, you know what? It's not quite as simple as it's all just matrix multiplication. It's really just all vector multiplication. So, what's a vector? A vector is really just a type of a matrix. It's a grid of numbers, but in this case, it's really a row of numbers, right? So it's x1, x2, x3, and on to xn. Or we could have a column vector where it goes from y1 down to yn. It's a list of numbers, right? It's a set of numbers in a particular arrangement. So just like with matrix multiplication, where we have to have the dimensions add up, with vector multiplication, in this case, what we also call a dot product, we're multiplying these two vectors. They have to have dimensions that match, right? So we're multiplying a row by a column because that means we're going to end up with something that is one row by one column out. We're going to get a single term, and that basically means we're going to condense all of the information we have in these two vectors into some single number, which might turn out to be really valuable for some model. The really simplest way of putting this is a really simple thing to do with the right notation. So z is the sum from I equals 1 to n of xi times yi. Now what does that mean? That means x1 times y1 plus x2 times y2 plus x3 times y3, and so on all the way down to xn plus yn. So we are multiplying each element with its corresponding partner, and then we're adding it all up, right? So we are getting n different products, but because we're adding them all together, they compress down into this one single number. So that is what we're doing with each matrix. So this is why we need, what did we say? We had 3 by n, and this was n by 4. We need these n's to match up because we are taking this vector, which is just a row from our matrix, and we are getting its corresponding dot product with the vector from this column in this matrix. Now this is all very abstract. I'm right there with you. This is pretty weird, but I want you to revel for a second. All that abstraction means that we can really capture a lot with not a whole lot of ink. What we've got on this page really captures what matrix multiplication is, at least in terms of the mechanics of it. Not the intuition at all, but all the rules that you'll see in Khan Academy and textbooks, all these things about A11 plus B22 and all the arithmetic of it, I think can really overshadow what's really going on, which is just kind of this merging, right? So I kind of imagine these two vectors that we're pushing together into this one number. I just kind of imagine like if you had two pieces of Play-Doh that you just mushed into something new, right? We're kind of compressing that. Now, a specific place we see that is if we're looking in a statistical model at the sum of squared errors. This is basically like a way of getting, say, x times the transpose of x. gives us x squared. If x is the error from a statistical model, we do that, we get the sum of squared errors. We are getting the squared error for each prediction from the model, and then we're adding all those errors together with this dot product. So the dot product is also a really nice, simple thing. So on the one hand, I kind of feel like this 3 to 4 matrix multiplication, for me, having gotten comfortable with this, this feels like the easy way to do it. But on the other hand, it is really just made up of this, and you know, this is kind of comfortable too. When you get used to this notion of you're just rolling together these things, they kind of fit together like gears. You get those multiplication, then you add them together, and you get some number out of them. That works as long as you got the same number of teeth in your gears. All right, dot product, no big deal. So what did we do here, and how does that match up? So what we did here when we multiplied these specific examples is we got 3, 6, 7 in these top two elements and 2, 9, 11 in the bottom two, right? So we match the rows from the first, which is just the rows from the first, against the columns from the second, 6, 5, 3, which we had to turn to match up with this. Felt a little bit weird turning these from a column to this, but again, we're just matching 3 by 6, 6 by 5, 7 by 13. We add them all together. It's kind of clunky when you're writing it all out like this, but fundamentally, it's just the dot product of whichever two vectors are intersecting in this. We take the outer rows, we take the rows from the first, the columns from the second, we ask what are the dot products at each one of these points. So that is the rules of matrix multiplying, right? We are just doing those dot products in order, which is a real pain to do on paper, but like we saw, it's easy to do on the computer, right? Especially when you're not manually defining your matrix one at a time, but you're pulling it in from some sort of data set. All right, so that is really the simple stuff that we need to see about the actual mechanics, the sort of pen and paper math of matrix algebra. For the rest, you'll see some stuff in Khan Academy that will touch on the importance of this, but really my goal here was just to show you that there is this tool. And like we said before, for particular tools, this is incredibly valuable. If you're not doing these things, it's kind of a lot. And the first time you take a linear algebra course, it's kind of tough to get into your head. But with repetition, with practice, and with actually applying it, and I particularly personally really built some intuition on linear algebra by doing courses in neural networks. The tools of linear algebra are really useful for building these large-scale models, which is what we get with complicated statistical models. But it's also applicable in things like network models, which is another thing that I find interesting. And so having the tool of linear algebra just opens up venues for my exploration. It's a way to scale up the sort of math you're doing. So I would encourage you to look into this more now that the semester is done, but we're not going to worry too much more about it for this class.